So in this video I'm going to give a homological proof of the fundamental theorem of algebra. Now remember what this says. It says let P of Z be a polynomial of degree n greater than 0, say, with complex coefficients. Then P has a complex root. Okay, so there's a whole number of different ways of proving this, but we're going to do one which uses homology theory. Okay, so for that, we're going to use the homology of the circle and of the punctured complex plane. So we proved earlier, in two different ways, in fact, that the homology of the circle, which of course is the same thing, the first homology of the circle, which is the same as the first homology of the non-zero complex numbers, it's the it's copy of the integers generated by a certain element u, where u is the actually let's call it square bracket u here. So here this is the map from the unit interval to S1 given by u of t is e to the 2 pi I t. Okay, so we proved using Maya-Vietoris that the first homology of the circle is a copy of Z, and then we previous to that we used kind of methods of complex logarithms and so on to give a different proof that H1 S1 is Z using this kind of loop here. And as part of that proof, we also showed that the n times this, actually let's call this one u1. So n times u1 is the same thing as has the same homology class as the loop un, or let's call this m because we've got n was the degree, so call this um. M times u1 is the same as square bracket um, where um of t is just e to the 2 pi I mt. Okay, and so in other words, if we define Fm from S1 to non-zero complex numbers by Fm of Z is Z to the m, then we see that Fm lower star of U1 is Um, or okay, let's do it with square brackets. That's square bracket Um, which is m times the square bracket U1, and the main thing we just need is that it's not 0. Okay. So if we just look at the mth power map, then on homology that's just multiplication by m. So now let's consider a map G, say, from S1 to the non-zero complex numbers, which isn't just equal to the Fm that we just considered, but is reasonably close to it. So I'm going to suppose that, so remember here, we're looking at the distance between Gz and Fm of Z. Fm of Z, remember that was just Z to the m. And let's suppose that that's less than 1. Rule Z. Okay. So now, of course, this Z to the m is on the unit circle. You know, Z was on the unit circle. Z to the m is on the unit circle. And so the closer, So let's draw a picture maybe. Here's our z to the m. Here's 0. And we're assuming that we draw a circle radius 1 around here. So our g of z is somewhere in here. You don't know exactly where it is, but it's within a distance strictly less than 1 of z to the m. And so in particular, this if we look at the straight line joining g of z to fm of z does not pass through 0. You draw it here, wherever it is. Could be there, whatever. But you do a straight line between z to the m and g of z. It's not going to pass through 0 because it's too short. So we have a linear homotopy. HTZ is 1 minus TGZ plus TFM of Z. So between FM and G, as maps from S1 to non-zero complex numbers, and that means that G star is the same thing as FM star on H1 S1, i.e. G star U1 is MU1, which is non-zero. Okay, so if anything's sufficiently close to the Z mth power map, then it will also be non-zero on homology. Okay, so now to return to the fundamental theorem, let's suppose, or a contradiction, that P of Z is a polynomial of degree n bigger than 0 with no roots. Okay, then now choose a sort of very large R. Okay, we'll specify a bit later exactly how large it has to be, and we'll define G from S1 to non-zero complex numbers by G of Z is going to be P of RZ over P of R. Okay, so this is valid because so P has no roots. So both PR and PRZ are non-zero, so it's meaningful to divide, and the answer is non-zero, so this is a genuine map into the non-zero complex numbers. Okay, so that's a map, and then we can also define H from 0, 1 cross S1 to non-zero complex numbers, just by H of T comma Z is same sort of thing, P of RTZ over P of RT, which is also So we know that if we do h of h0z is just equal to 1, right? Because then there you've got t of 0, you just get p of 0 over p of 0. And h of 1z is g of z. Therefore, g is homotonic to a constant. That means that G star is going to be 0 on the homology of S1. But that's going to contradict what we had before. So space. Now let's suppose our P of Z was A0 plus A1 Z up to AN Z to the N. And it was supposed to have degree n, so the last coefficient an is supposed to be non-zero. Then if you look at this P of Rz, R very large, an R to the n, Z to the n, that'll be much bigger than all the other terms, right? If R is 1,000,000, then here this is 1,000,000 to the power n, and then next one down is 1,000,000 to the power n minus 1, which is about 1,000,000 times smaller. Of course, that could be reduced by if depending on exactly what the coefficients are. But we could be a little bit more precise if necessary. But basically, this is the point. As R is large enough, then this term will completely dominate. And so our G of G of Z, which is P of Rz over P of R, is going to be approximately Rz, or an Rz to the n, R to the n, Z to the n, over an R to the n, which is Z to the n, which was our Fn of Z. Okay, so I'm not going to try and make this precise here, but one could do, and then you find that we find the distance between G and Fn is less than 1, and therefore G is homotopic to Fn, and as we described previously, that gives us G star of U1 is 0, is U to the n, is NU1 that contradicts our previous proof that G star is 0. Okay, so we've got a contradiction. So this P of Z with no roots, that can't happen. So we see that every complex polynomial of degree at least 1 has at least one complex root.